Wow. Okay, wait. Is my microphone working? Okay, I think my microphone is working and I am live. Well, hello there. It has been quite a while. I've been away. Uh, so, what has happened and why have I not been live streaming? Number one, for the past month, I was in Asia. So, I was vacationing and I went to Korea, Hong Kong, Macau. So, I spent some time with family and just traveling, so didn't have as much time to live stream. So that's excuse number one. And number two, as part of the bigger picture, I guess some of the things I've been doing, I kept telling myself that I don't really want to live stream it. Um, for example, today, learning about probability, um, which is not directly related to what I was trying to do with reading research papers, which is why I was recording myself like building models or like writing ML models from scratch, which I'm going to continue to do. But I think the bigger issue was sometimes there would be some things that um, I would I would want to do, for example, this probability stuff, and I would be afraid of going live and showing how little I know about a particular topic. So even in the machine learning stuff, I think like there's some certain topics which I feel like should be very easy to understand, and yet what's an example? Like maybe like random forests, like have some idea of how it's implemented, but like no, I don't think that's a valid example. I can't think of an example right now. Um, but perhaps like this probability one, right? So today what I wanted to do was do some practice in probability because I find that this is an area that I'm lacking in. Um, so I took a statistics course in second year of university, but uh, I know sort of the formulas and how things are applied. But when it comes to solving problems, I find myself being sort of slow or like just not being really good at solving a particular problem. And you know, I I've always wanted to practice this stuff, but I didn't see myself like live streaming this, and I was afraid of being judged and being perceived by people who watch these. And as I've started to gather a non-zero following, although there's probably still like nobody watching, which is great. Um, I don't really want people to watch my stuff because it's more for me to document myself. Right, so the live stuff here, but I don't know. I'm also conflicted. I do enjoy like building in public, and I really want to continue building in public. So all this ramble to say that uh, there has been some mental barriers in me live streaming, and I am doing my best to get over these mental barriers, these limiting beliefs in myself, and this being afraid of getting judged by other people when they see like me live stream and seeing like, oh, this guy's actually not that like cracked or technical. But um, when you think about when I started YouTube and when I started doing all of this stuff building in public, it was never to establish myself as someone who is knowledgeable, but rather to share my love and desire for learning and improving, because it's not about your destination but about the process of getting there. And at the same time, as I live stream, I am able to get better at articulating what I know and teaching and sharing and inspiring. And so that is the main thing that we should focus on, and not like, oh, are people going to think about me uh, when I put this stuff out there, right? Because you cannot control that. But what you can control is, I guess, like your own sort of mindset. And okay, sure, you can control, so you can sort of help shape what people think of you by deciding what you share. Um, but I think overall, I'd like to share more than less, right? The more I share, the oh shit, I have a phone call from Timothy. Okay. Give me 1 second. Okay, I need to step away for 2 minutes to pick up my badminton racket. Uh, I don't need to leave the house, but my friend's waiting for me. So I will be back in 2 minutes, and we're gonna keep going with the live stream. Okay, I'm back. Here's the racket I got, strung with the BG65, I think. Okay, anyways. All right, another side tangent, which is that when you do these things, it's like a muscle. So the more at first it's really hard. It's just like me like going live streaming again. It's like really really hard because I haven't done it in a long time. So it's just the more you do it, the stronger the muscle gets. And another thing is when you live stream and you say things, you saying things reinforce your brain much better than if you're just thinking, or like you are what you think basically. So yeah, you can think it or you can say it out loud. So in this case, I'm saying my beliefs out loud, which reinforce my beliefs, which are good because uh, I shape myself into the person I want to become. And the last thing before we go into this probability stuff is I still want to improve at explaining, because I find that oftentimes it's I'm not explaining things as clearly, and I want to improve on the intonation, the use of my intonation, because a lot of time I can sound very monotonic. Just like at the very beginning of this video, or of this live stream, I'd say I was rather monotonic, whereas like talking like this and very flat and very sort of like not engaging, which is bad. So how do we fix this? Number one is getting better at projecting my voice. So using my chest more than like my mouth, because I do find that sometimes I sound pretty nasally, like it's like talking to my nose. But anyways, there's just something to be aware of as we live stream, and we're gonna get better with this. So the topic for today is probability. The reason I want to study probability is because, well, one, it's like a really it's useful. It's a very useful skill if you're doing ML, machine learning, or even a lot of my friends are doing quantitative finance. So it's useful for interviews, but more generally, it's foundational, right? Like when it's a very useful life skill. Like whether you're playing poker or whatever, life is not deterministic. There's always different. It's always a calculated risk, and if you're able to sort of like quantify these, then you are able. It's just like a very useful skill. So I took my second year course in statistics called like Stat 206. You can see the note here, and you learn like your probability distributions and the basic probability rules. So there's statistics and there's probability. I think today I just want to focus on probability. And so probability is essentially just like knowing how to count essentially. I think like there's a few very basic formulas that you need. So I'm gonna write these down in a second. Okay, let's review like the probabilities real quick. So I can go over here. So I think number one is just like conditional probability, right? So you have like P of A given B, and this one is equal to P of A and B divided by P of B. And the way I sort of visualize this is to this Venn diagram, right? So you can imagine event A and event B. So the intersection of these two events is given by this. And when we're saying what is the probability of A given B, that is, what this says is like, okay, let's say event A happens. That would be just P of A. But we're saying, what is the probability of A happening when B has happened? And I think like when I was first learning statistics, and maybe even now, like sometimes it's very confusing. Like, what is the difference between P of A given B versus P of A and B, right? So P of A given B is always, if we just look at the formula, it's like always less or equal to P of A and B, right? Because what is P of A given B really saying? That's saying if B is guaranteed to happen, like if we know B happened, what is the probability that A also happened, right? Whereas P of A given B is just saying what is the probability of both events happening. So one is anticipating that B is already going to happen, and the other one is saying, okay, what is the probability of both events happening simultaneously? So P of A given B, or P of A and B is given by that intersection. But if we're saying P of A given B, what we're saying is we're assuming that P of B is going to happen, right? So that's given by P of B. And we're saying, okay, what is the probability that A happens when B has already happened? And it's only given by this darker, or like this intersection. So that's why it's P of A and B given by P of B and not P of A, because anything here cannot happen, because this part that doesn't intersect with B, like it only happens when B did not happen. But here we're asking what's the probability of A happening when B has happened. And so it's essentially a fraction of like, okay, first you need to know what the probability of B happening, right? And like if you were to just say P of A given B is equal to P of A and B, that would be a much smaller number. Wait, am I saying this correctly? P of A given, or I'm being stupid. It's like this, because we're dividing by P of B, which is always less or equal to 1, right? So then P of A given B will be greater. So P of A given B is always going to be greater than P of A and B, because if we were to say P of A given B is equal to P of A and B, that just means that if we're assuming that B is to happen, what is the probability of A happening? And here we're saying what's the probability of A and B happening at the same time, but it fails to see that it's like under the condition that B is happening. So you divide it by P of B just to normalize it, like, oh, only in the space of B happening, right? So if B never happens, then if B is a very, very small probability, then P of A and B is a very, very small probability, right? But we're saying if we're asking for P of A given B, then we like assume that B is going to happen, even if it's a very, very small probability. You need to like take P of A and B divided by P of B. Okay, that was a very long-winded explanation for this first rule. So this is just like conditional probability, and I guess you can rearrange it to be P of A and B is equal to P of B times P of A given B, right? Yes. And how do we visualize this? So it's P of A given B multiplied by this smaller probability, so that gets rid of P of A and B. Yeah, if P of B is 1, then P of A given B is equal to P of A and B. Okay, that's the first rule. Then I guess you can swap the letters, because P of B and A, these are commutative. And okay, what's the other rule? Okay, Bayes' rule is the one that I always like forget, and I need to refer to my notes. And then yeah, like I think like if you don't know Bayes' rule by heart, like if someone doesn't know Bayes' rule by heart, I think like they're not very good at statistics, right? Like that's like the basic. That's like asking, do you know what 5 plus 5 is? The equivalent in like probability or statistics. So yeah, I've learned it. I've seen it many times, but I always forget it. So what is it? P of theta given x is equal to P of x given theta times P of theta over P of x. Okay, where does this come from? That is, I think the derivation is very, very simple, right? So like, we know that P of, okay, let's use letters. Like basically, we want to write P of A given B in terms of P of B given A, right? So we know that P of A given B is equal to P of A and B over P B, which is equal to P of, which is equal to P of B given A times P, times PA over PB, right? And then that's basically, I think that's Bayes' rule, right? Okay, there we go. That's Bayes' rule. I just derived it like that. So it's just useful because you can rewrite, you can sort of like flip these two around, like, and then you can use this for deriving, I guess, more complicated rules. And one side note, right, when learning these, what I'm focusing on is building better intuition, right? Like building a very strong understanding. Like you can memorize these rules, and when I was taking this course, you know, it's like mostly memorizing these rules, but getting this deep fundamental intuition of like why things work the way they are, like truly understanding something, takes a lot more effort. And I really want to focus on understanding, right? Not just like blindly copy pasting a formula and doing like pattern matching, because that stuff is like kind of easy to forget, and that stuff is like you're not actually deeply understanding the topic, right? Okay, so that's Bayes' rule, and let's go back to our textbook, or like this exercise. So chapter 4, probability theory, foundation of every, okay, sure, like okay, we don't care about this. Okay, so outcome, sample space. This is just some definitions. The outcome of an experiment, the set of all possible outcomes, that's your sample space. Probability is between 0 and 1. A set of outcomes. An event is a set of outcomes and subset of the sample space. Okay. So yeah, I don't know what the difference between an event and outcome is. Let me ask chat. Okay, so sample space is like everything possible. Is an outcome. A sample space, every possible outcome is like a possible result, an event is a set of outcomes, okay. And it's a subset of the sample space, okay. And mutual exclusion just ensures that these two are independent, okay. That's not hard. Random variable that maps into the set of real numbers. Okay. Okay. So let's do these exercises. Two gamblers are playing a coin toss game. This gambler has n+1 fair coins. B has n fair coins. What is the probability that A will have more heads than B if both flip all their coins? Okay. So yeah, I think my problem is, like, I read this question, I understand the question, but I have no idea how to approach it, right? So let's say, like, if they had if both had the same number of coins, then what I usually try and reason about is, like, okay, let's look at our like, is it called sample space? All right, like, yeah, what's our sample space, right? And then you sort of reason about, like, what is in this sample space, what is the probability that, you know, something happens, right? So, like, in this case, you have, like, gambler A rolls. Yes. Wait 1 sec. Display capture one. Okay. Sometimes it just glitches for some reason. Is this okay? I'm too small. Okay. Okay, I guess I make my face bigger. In this case, you know, gambler A, then B, then well, if you actually look at the tree, like, it's like A, then, like, A does a decision, then B does a decision, then A does a decision, right? So at the end you have, like, 2 to the 2 times n plus 1 events, or, like, possible like, combinations where if order matters, right? But in this case, like, we can actually simplify it to, I believe I can simplify it to just like A rolling a dice, then B rolling a dice, right? So you only have, like, 0 0, or, like, a coin, sorry, 0 1 1 0 1 1. Right, and so this is, like, like, if you're getting heads or tails, right? So you can see that, like, in 50% of the, actually, like, there's only this scenario where we have more heads, right? So there's 25%, and then the next time you roll, it's IID, right? Because it's like, it doesn't depend on the previous, right? So every time you only have a 25% chance of rolling that. So, but, like, can I just, like, ignore that and say that it's 1 in 4 chance? That's the intuition where it's kind of lacking. It's like, can I just say it's 20? Like, if I'm just simplifying the problem, instead of n+1, I'm saying if it's n fair coins, what's the probability that one person will have more heads than the other? I believe it's more than 25%. Like you can ask a bunch of questions, like, what is the probability that they have the same number of heads and tails? Like, that's why, like, my solution would be 2 times 2 to the n plus 1, right? That's the, like, the number of possible events, possible outcomes. Okay, if we're looking at the original solution, right? And we're looking at, okay, what's the number of events where, or what's the number of outcomes where they have the same? Well, you have, out of your n tosses, right, you need to choose you need to choose n over 2. Alright, so like if you have if I'm saying you have slots 0, 1 to n, you need to choose n over 2 of these, so that the other n over 2 are tails. Oh wait, no, this is not even correct. See, this is why I freaking suck at this. And, you know, it's okay. I think, like, it might be obvious to some people because you have had the tools and you've seen how to do this. And I have seen how to do this. But I'm struggling at the moment because I really suck at counting, which has been made even more obvious just to me right now. Like if there's a single coin toss, you can just count it very easily, right? What's the probability that A will have more heads? It's 1 in 4, right? Because there's only this event. Or sorry, I guess like I should circle this because it's asking A will have 1 heads. Now if there are 2 coin tosses, then A and B, you have like the same situation, but now what happened is like, even if you got, like, you don't have to have this. This works, and this works. So actually, now 1 out of 2. You have 4 out of 8. Actually, it's multiplied. So this one, there's 3 events like this. And this one has to be this. And then this one just doesn't work. And this one has to go with like this, right? So you have 2 plus 3 over 16. It goes 5 over 16, right? So that's like how you count it. So I just manually counted the different set of possibilities, right? There's, wait, am I doing this right? Yeah, because from here you have 4 choices. From here you have 4 choices. From here you have 4 choices. From here you have four different combinations. There's like 16 combinations, right? Because it's 2 to the, or 2 to the 4. Just making sure I'm not being stupid. Because this is 2 to the 2 and 2 to the 2. So, okay, I'm in my head right now, and so it might not be clear to you guys what I'm doing. But if we're asking the question if like n is equal to 2 and both gamblers have the same number of fair coins, what's the probability? It'd be 5 over 16, right? And this is just manually counting the probabilities. But when you have n, it does seem a lot harder. So, okay, without looking at the solution, what you need to do is I guess like, generally there's a few tricks, right? Statistics. So I have it here. Probably number of elements in A or number of elements in S. Logically, relative frequency, Bayesian probability, 4-part method. See, this is the method: sample space, event of interest, compute outcome probabilities, and event probabilities. All right, which is what I'm trying to do for this. But yeah, I'm struggling to count. Okay, so let's look at the solution because I'm spending a bit too much time. Yeah, if there's symmetry, there's a lot of nice properties. But okay, let's say there's symmetry. Can I solve this problem? Because I was struggling to solve it even when n was equal to 2. Because if you look at every time, you have 1/4 chance of +1, 1/4 chance of -1, and 1/2 chance of contributing 0 to the sum for each given n, right? I guess that's how you see it. And if you go from 1 to n, right, you can basically boil it down to 3 events: +1, +1, -1, and 0. And then these are 1/4 chance, and these are 1/2 chance, right? And so you just want, like, when this happens n times, for the sum to be greater than 1, right? So let's first reason about the symmetric solution. So so if it's +1, like, how do we avoid double counting? Well, we can just do, I don't know how to count this, but yeah, in my head it's like 0, 0, +1, and then you look at the sum. I mean, this is just 0 and 1. Like, it doesn't change anything, but you would count this and then look at that. Okay. All right. What does the textbook say? Yes, that's right. Yeah, n coins with B's n coins. Okay. So P of E1 is equal to P of E3. Okay, so one trick that what did I do? Didn't do that they did is they actually broke it down into just like 3 events, right? And when we have symmetry, you have like A has more, B has more, and then B have same. Because it's symmetric, P of E1 is equal to P of E3, right? And so that's what they did. Of course, when you sum all these, P of E1 plus P of E2 plus P of E3, you also get 1, because this is all the possible events, or all the possible outcomes, and each of these are mutually excluded. And the outcome 3 possible. But this, so P of E2 doesn't matter because no matter, well, it does matter, right? Because there is a 1 in 4, well, there's a 1 in 2 chance that you get ahead. So it's like 2x plus 1 over 2y, where y is equal to 1 minus 2x. I see. So you don't actually have to compute the probability. And for the x's, for this event, we need to actually multiply it by x times, so one of them, it doesn't matter at all. Alright, no matter. And then the other one is x times, it does matter when you have, if you have less coins than b, then no matter what, it won't happen. So it's actually x plus 1 minus 2x equals 1, and now you have x 1 over 2 minus x equals 1. Wait. Wait, okay, so wait, that's what I did. Am I being stupid? Plus 0.5 minus x. Yes, that's what I did. X was 0.5 minus x equals 0.5. Oh, it's not equal to 1. Okay, that's the answer. So the probability is given by x. I see. Okay. I sort of get the idea. So you can instinctively look at this. So first, when you have one is, okay, learning number 1 here is exploit symmetry. And reason through cases. Okay, so this coin toss is actually not that hard, right? So when we have symmetry, then we just have like 2x plus y is equal to 1, and then when we see that, and then like y is equal to 1 minus 2x, right? And then because you know that the sum of probabilities is equal to 1, and then you replace y, and then you multiply by 1 over 2 because there's like a half chance that you get ahead. And then for the other one, you know that and I guess like you can just assume without loss of generality that like you get your first n coins and you get your n plus 1 coin, right? And that is the same as like saying like it doesn't matter, like you don't want to double count. Like, how are you ensuring that you're not undercounting? Yeah, that's how you, okay. Sorry, I'm just trying to make sense in my head. I was just picturing if you have n and then 1, right? Because we're like assuming this, so E1, E2, E3 happens in n, and then we have this event, so there's only 2 events, like Either we get a head or we get a tail for A, because only A gets to roll, right? So this is 1/2 and 1/2. And then we're multiplying things by these two. And then I'm saying like, oh, what if you viewed it like this, right? Like, it's just a different way of viewing the problem, but the probabilities will be the same. But if you count both of these, then you're double counting, because like the one here, it's already accounted for in your events. That's why you're double counting. Okay, let's look at the next problem. Card game. A casino offers a simple card game. There are 52 cards in the deck with 4 cards for each value. Okay. So what's our probability of winning, right? Like, my intuition is like there's also symmetry, so like if we pick 2 for a given card, the dealer has 3 out of we win if they pick like for 2 there are only like 4 cards out of 51. For 3, because there's only aces, right? Oh. For 2 we have 0 chance of winning. For 3 you have 4 out of 51 out of winning. For 4 we have 8 over 51 chance of winning, etc. till ace. And then I would sum these. And each of these have equal probability, right? So it doesn't matter, so it's just a sum over, I guess it's the average of these. Ends up being the average of these. 4 plus 8. You have all this divided by 13 types divided by 51. Alright, so you have aces the 13th, and so it's 12 times 4, right? Yeah, well, you have 48 chances, yeah. 13 over 51. Okay. That's my answer. Okay. Yeah, I solved it. Okay. That's basically the answer. Oh, sorry, I didn't share my screen. But yeah, this is, so it's 10 times 51 to 4 times 2's My solution is not clean though. Alright, because you have 1/13 chance for each card. Yeah, I guess the clean way to do it is like over 13 times the sum of 0.4 times 4/51. Yeah, 0/51 plus. Yeah, okay. Alright, quite easy. Okay, this is straightforward and it elegantly uses sum. It's not the most efficient way. Okay, I see. Okay, we can just exploit symmetry. Higher, lower, same. So same is just like 3/51, right? Hmm. 8/17, right? Okay. I see. That's how you do it. For any given card, the probability is 3/51, so it's 1/17. Okay. Okay, we get the spirit. Okay, let's do a timer. So a stopwatch, so we can see how fast we can solve a particular problem. Because here, speed also is also important. All right, let's go. 100 airlines are waiting to board a plane. They each hold a ticket to one of the 100 seats in the flight. For convenience, say the nth passenger in line has a ticket for number N. They jump the first, picks a random seat, and we'll go unless it's already there. Okay. I understand the question. How do we even solve this, right? There's only a 1 in 100 chance for the first one to pick the right seats. Well, I think like if the drunk person doesn't pick the right seat, then someone it takes someone else's seat, and someone else will take someone else's seat, and then you close the circle, right? So it's essentially just like there's only 1 in 100, I think, because the drunk person has to take his own seat. If he doesn't, then it doesn't. Then at some point, like the next person gets a seat, right? But if he doesn't, if he takes your seat, then you know that's one of the probabilities. If he takes someone else's seat, someone else will take someone else's seat until it's. You have to make a cycle because everyone gets a. Hmm? Like we're the last person to board. Oh, I guess the cycle can close earlier. The cycle closes when the person who can't get their seat will go to seat number 1. So it's more. It's less than 100. Sorry, I'm being stupid. Okay, so how do we? C1 is together. Do this. Okay, I don't get why this is symmetric. If seat number 1 is taken before number 100, then the cycle is closed, so you can get your seat, right? And it's because you take a random seat. Yeah, I get that it's symmetric. Wow, it's 50%. Wow. Okay, next question. Okay, understood in 5 minutes. Alright, next question. Given endpoints are drawn randomly on a circumference of a circle, what is the probability that they are all within a semicircle? Oh. Oh, I see. All within a semicircle. So like radius of a semicircle. Okay. What are the events like? think it's just you set a point, and then, right, it doesn't matter where the point is, and then you look at the n minus 1 points, and all these n minus 1 points have to be within the radius, so they all have 0.5%, so it'll be 0.5 times n minus 1, right? So because the first point doesn't matter, no matter where you start, it's the same probability. Okay, n over 2 to the power of n minus 1, right? N over 2, oh, wait. Yeah, okay. I don't understand this explanation. The events that okay, so this is 4.1, which is just counting to events, right? Like to sets. Okay, and then next is the technique of like combination, symbol counting. Coordination, combination, binomial theorem. Inclusion exclusion principle. I didn't cover this, but this is pretty simple. Yeah, let's look at this. Hands with 4 of a kind. I mean, it's 5 choose 4. Wait. It's 4 times 3 times 2 times 1. So that's times 51 minus 52 minus 4. And last card, where order doesn't matter. Times 5, because there's 5 different slots. This is the number of ways you can make a 4 of a kind with your 5-handed, and then the total number is 52 times 51 times 50 times 49 times 48. Order doesn't matter? Okay, that changes a lot. It's 13 times, if you fix a club, you have four of a kind. Full house is 13 times 12, and order doesn't. So then it's 13 choose 2. 4 choose. That's 2 different numbers, and then four times 4 minus 4, 12. How do you get 12? Because 4 times 4 is double counting. You're saying ace, that's 4. No, it's not double counting. Yes, it is. No, it's not. for the first one you have 4 choose 3. That's 4 choose 2, right? What, isn't it divided by 2? Because full house is... Oh, it's not choose 2. Because the order matters. This is the numbers and these are the clubs. Hands with 2 pairs. Uh, 5 card combination. 13 times 12 times 48, because you took 4 cards. And this is actually 13 choose 2. Because they're the same. Also be 4 of a kind. And then for these you need 13 choose 2, you need to multiply by 4 choose 2 times 4 choose 2. Because they need to be different. How is it 44? Oh. Wow. The last card could have you move 4 cards and there's 2 other cards and 2 other cards. There's 4 other cards you cannot pick. Wow. Okay. Let me take a break real quick. Okay, let's keep going. It's been an hour. Okay. Hopping rabbit. Our rabbit sits at the buckets, and also let's start our timer. Stopwatch. Alright, it sits at the bottom of the staircase with N stairs. The rabbit can hop only once, only 1 or 2 stairs at a time. How many different ways are there for the rabbit to ascend the top of the stairs? Oh, okay. So I usually, this is like a LeetCode question. Or you can break this. You just like, it's like the number of Fibonacci sequences. It's just like you do DP and then at the top there's only, you set your base cases. And then n-3 is equal to n plus 1 and then number of ways n plus 2. I guess there's an analytical solution here. Like if you're n minus 1, you have one way. If you're n minus 3, you have it. If you're n minus 3, it's n minus 1. It's like 1 plus 1. Let's see, n minus 4. Yeah, it is Fibonacci, right? Okay, it's pretty easy, but okay, so there's no analytical solution. Okay, I'm tripping. Like, okay. All right, next question. How is this like the category? Okay, sure, whatever. Oh, also I need to understand this. I mean, majority, like, isn't 6 locks? Oh, this is hard. If you have a lock, and if you have 6 locks, and each part has their own lock, like, the new solution is like there's 12 locks, right? Um, if you have 12 locks, and you can open that and that, and that with that person. I have no idea how to do this. Like, I don't even know how to do this. Hmm. 6 factorial. Okay, need to do reflection soon. Why is it 11 factorial over 6, 5 times 6? Because why does order matter here? Also, yeah, like. Yeah, well, there's permutations. Why is it? Oh, wait, I'm being stupid. 11, this is equal to this. Okay. And we're overcounting it, right? So how many ways can you arrange it? It's 5 factorial ways. A unique 6-member subgroup. Okay, next question. The player with the better skill always wins. What's the probability that player 1 and 2 will meet in the final? Well, player 1 will always make the final, right? Because player 1 always has the highest skill. Now, what is the probability that 2 will make the final, basically? So 2 will make the final if it runs into anyone but 1. So I guess it's like, what's the probability that 1 and 2 don't meet until the final? Right, so you have so that means that. Alright, so if there are 2 n players, there are n rounds. So in the n minus 1 round, in the n minus 1 round, you choose so 1 doesn't meet, and 1 and 2 meet. And this is given by n minus 2 over 2n. To the 1 minus 1. Wait. How are you supposed to look at this? One minus, if they don't meet with a final. I'm getting tired. Yeah. Yeah, I was getting to something. Okay, I'm gonna take a break. Might continue. I need to get dinner too. Yeah, why is my voice like getting lower? Okay, and then this is probabilities, discrete and continuous distributions. Oh yeah, this is interesting. Okay, I think I can. Let's try to finish this today. And let's be really intentional with each problem, like why I can figure it out and how we can figure it out faster.